Hello guys, welcome to my channel, and in this video I'll explain to you article number 2.4 potential due to an electric dipole. This is the fourth lecture of the fourth video of the second chapter, electrostatic potential and capacitance. So in this video I'll explain you what is the potential due to a electric dipole. Dipole, as you know from the last chapter, it is a 2 point charges separated, equal and opposite charges separated by some distance, some finite distance. Okay, this is a dipole. Okay, now we'll study the effect, the potential due to this dipole at a general point. In our previous video, we talked about what is the potential due to point charge. So let's start. As we learned in the last chapter, an electric dipole consists of two charges, q and minus q, separated by a small distance 2a. Its total charge is 0. Okay, so total charge of the dipole is obviously 0 because minus q and plus q charges are on the dipole. Okay, it is characteristic by a dipole moment p whose magnitude q times 2a, and which point in the direction from minus q to plus q. Okay, as you know, there is a dipole moment. If what is the magnitude of dipole moment? Dipole moment is denoted by p. It is magnitude is q times either charge times magnitude of either charge times the distance between the two dipole. Okay, and it is a vector quantity. Okay, the vector quantity, the direction is from minus q charge to plus q charge. This is the direction of the dipole moment. What is its physical significance that we studied in the previous chapter? It was, suppose I place the dipole in an electric field, it will experience a torque. So how much the torque? This is a torque experienced by a maximum torque experienced by a by a by a dipole when it is placed in unit electric field. This is the dipole definition that we have seen in the previous chapter. Okay, so you got an idea what is dipole moment if you haven't understand it there. Okay, so now we also saw that the electric field of a dipole at a point with position vector r depends not just on the magnitude r but also on the angle r and p. Okay, so what we have seen in, we have find the electric field due to a dipole at two position, an axial point and a equatorial point, and we see that it depends on r. So E for that was 1 upon 4 pi epsilon naught. For a small dipole it was 2p upon only magnitude r cube. Okay, and for this was axial, and there was also equatorial point. For equatorial point it was 1 upon 4 pi epsilon naught p upon r cube. They have different directions, so you see there it depends on the angle. At different points, at different angle, the electric field due to dipole was different. Okay, so it depends on the angle also. There was inverse cube relation for distance, and also angle dependence is there. Further, the field falls off at a large distance, not as 1 upon r square typical of field due to single charge, but as r cube. This is also true that I've seen from the formula. You can see for a point charge it was 1 upon r square is proportional to 1 upon r square, that is distance fall off 1 upon r square time. But for a dipole the distance fall off 1 upon r cube times. Okay, so we now determine the electric potential due to a dipole and contrast with the potential due to point charge. Okay, so in this video we have to find the potential. We have talked about potential due to dipole, and we'll contrast it with the what was the potential due to a single charge that we studied in a previous chapter. You can check it from the playlist. Okay, now as before we take the origin at the center of the dipole. Now we know that the electric field obeys the superposition principle. Okay, now what we do, we gonna take the center of the dipole as the origin. Okay, and it follows the superposition principle, that is the potential due to this one charge. This point we have to find the potential. So the potential due to first charge and the second charge, so what will be the total potential? It is superimpose. Okay, the total potential will this is just sum of these two. Okay, in electric field it was the vector sum of the two electric field due to two different charges, but here it is scalar quantity, we'll just add them up. Okay, and you can also state it like this, like the presence of the other charge does not affect the potential due to this charge. Okay, so this was the superposition principle, so we'll apply here, and in order to get the potential at this point, we find the potential at this point due to this charge, and we'll find the potential due to at this point due to the other charge, and we'll just take the sum because they are the vector scalar quantities. Okay, we'll take the algebraic sum of this. Now okay, since potential related to the work done by the field, electrostatic potential also follows the superposition principle. Okay, so as I told you, what is superposition principle? It also follows superposition principle potential. Okay, now thus the work potential due to the dipole is the sum of potential due to the charge q and minus q. I already explained this. So what will be the total potential? This will be the sum of the two potential. Okay, and you know the potential due to the minus charge is minus q. Okay, I can write it. Okay, so v is equal due to minus charge is 1 upon 4 pi epsilon naught minus q upon r2. R2 is basically distance, this distance between the point and the minus q charge. Okay, you can figure it out on your own based on your previous knowledge of what we studied in our previous lectures, previous articles. Now, okay, so this will the formula for the total charge. Now we have to calculate it in terms of, we'll have the distance will be like this. So what we are gonna do, we are gonna replace this r1 and r2. We'll find it in terms of this r, that is the distance from the center of dipole to the point we have to where we have to find the potential. Okay, so now, yeah, okay, now by geometry, this is a mathematics now involved, the derivation is there. So for this, you see, okay, suppose the dipole is at angle, the center from the dipole is at angle theta with the dipole moment, and this distance make angle theta. Okay, so now from geometry you see what happens here. You see, for a small angle, for this is a very small angle, what we can do, if I ask you how much this distance is how much, yeah, or this distance, that is r, how much r is greater than r1, so just drop a perpendicular here from this point, just drop perpendicular. So now they are equal. Okay, for small distance, for a small angle, this small angle, I can say that now they are equal. So this r1 is equal to this part of r. Okay, got my point? This r1 is equal to, if I draw the perpendicular, then this much. Okay, so yeah, so what we can do, so how much is this? We have to find how much is this, okay, because you know we are converting this r1 in terms of this r. So you see, if I draw the perpendicular, how much is this length? I want to know how much is this length. So you see, it is, because this is a, okay, and from trigonometry you can figure it out, this is a cos theta. So this is how much, this length is how much, r plus a cos theta. Okay, you got my point? This is r plus a cos theta. Okay, and now yes, okay, so this is r a cos theta, and what is this? This is, yeah, this is r a sin theta. Sorry, only a sin theta. This is a sin theta, and this is a cos theta. Okay, so now we'll see here. Okay, so r1 square. So what is r1 square? R1 square, from this you can see, this is what, yeah, this is, okay, how much is this? So r1 square, if I take the square of this is equal to r, what is this length? This length is, as I told you, this is r, this is a cos theta. Okay, and this is r. So I can say r1 square is equal to r plus a cos theta square. Okay, if you do on your own in a notebook, you will easily say that this is r plus a cos theta, and I am squaring on both sides. You will see why we are doing this. Okay, similarly, if you want to find this length r2 in terms of this, so what you're gonna do, you're gonna drop a perpendicular here. Okay, and this line will be obviously a cos theta. And now what is this r? This is r is, yeah, r2 is, no, yeah, r2 will be r minus, sorry, r plus, in this case this will be plus a cos theta. Okay, on squaring on side, both sides, this is, so this is how we obtain these two equations you see here. Okay, these two equations are obtained, and I will square them. As I told you, this is r1 is square is equal to r minus plus, sorry, I minus a cos theta square. On squaring you will get, just put the identity a plus a minus b whole square, so you get this and you get this. Okay, so now if we take r much greater than a, so for r very greater than a, the distance between the dipole and the points of concentration is very greater than the distance of the dipole, length of the dipole. So handwritten terms are only up to the order a by r. Okay, the square term will be very small, you will see how, and we'll cancel them out. Only a by r terms will be retained. So now, so this is, yes, so r1 square becomes what? This is r1 square. This is, I'll take out r square common. Okay, r square I'll take out common. So what remains is 1 plus a square by r square minus and 2ar 2a cos theta by r, taking r square common. Okay, and you see this is a square term. A square is, a is very less than a r, and I'm squaring it, so and this become very small, so I can neglect it. Okay, and so what I get is r1 square is equal to this much and r2 square is this much. You can see it yourself. If you do the same thing is applied here. Okay, and now you will use the binomial theorem. You see, what I'm gonna do is take the reciprocal of this. You can take the reciprocal of, suppose I'll do it for this. Okay, if I take the reciprocal, what I get, r2 square on upon, this is 1 upon r square. Okay, and this term will become, okay, one second, this term will become what? If you see this r2 square, okay, this is 1 upon r square, and what this becomes is, just one second, yeah, so this is 1 upon r2 square, 1 upon r square, and the reciprocal of this will be, I'll just do it like this, I'll take the power as -1. Okay, and on taking the square root on both sides, the square root will be cancelled on this side and this will be -2. So this is how arrive at this. Okay, this is how arrived at this. You see here, this is how arrived at this. Okay, -1 by 2, sorry, I've taken the square root, so I write in the power, in the power I write -2. That is not -2 because I'm taking the square root, that will be half, so -1 by 2. I'm sure that you have understood this. Okay, similarly for this you can do, you can do this. Okay, now you know binomial theory, you are studied in class 11th. Okay, so if I apply binomial theorem, so what will happen? So this -1 by 2 will be multiplied. Okay, so what happens is this will become 1 upon r, you can see from here. Okay, 1 upon r, 1 minus, this will become, the -1 by 2 will be multiplied here. Okay, and this will become plus and 2a r cos theta. Okay, so this is the result. Okay, so not, sorry, 1 upon r, yes, 1 plus, because -1 by 2 is multiplied with minus. Okay, 2 by 2 a by r cos theta, applying the binomial theorem. Okay, so if you know binomial theorem, 1 upon x is what? Power 1 minus 1 is just simply multiply this -1 by x. This is the how we apply the binomial theorem. Okay, now next thing is, similarly we'll do it here, and we'll get 1 upon r by r2 is equal to 1 upon r, 1 minus a by r cos theta. This is just the mathematics that you have to deal with. So now we have got 1 by r1, we got 1 by r2, and we had that equation. So what I'm gonna do, I'm gonna put those two values in this equation, 2.9 equation. Okay, so when I put these two values there, so you can see here there is a subtraction in there. Okay, so what will happen, I'll just do it here. Okay, this will be minus, okay, after this will be minus 1 by r. Okay, and yes, 1 minus a by r cos theta. Okay, I'm not writing the whole thing. So this minus will be multiplied inside. Okay, and you see this -1 will be cancelled out with -1. So what remains is, I can write it like this. Okay, I'm sure you have understood, but still I will write 1 upon, I'll just multiply this inside, 1 upon r a r square cos theta. Okay, then for this term -1 upon, using the above equation. Okay, there is a minus there, 1 upon r a plus a by r square cos theta. Okay, then this will cancel out. Okay, and this will add up, so this will be 2a cos theta by r square, or I can still write this in this form. Yeah, so this will become You see, q 4 pi epsilon naught was there, 1 upon 4 pi epsilon naught was there. Q is common because the charge is same for both. Okay, and now this is q 4 pi epsilon naught, 4 pi epsilon naught, and I have solved this for you just now, and you will get 2a cos theta. And you know q into 2a is what? P. Okay, dipole moment, I just told you P, dipole moment cos theta upon this term. And I can write this in vector form, you have to write. So this dipole moment I can write as P dot R. Okay, I can write this like this. Okay, so this is the, in vector form I can write it like this, where R is the position vector from OP outward. The position vector is outward for a positive or obviously. Okay, so unit vector is the direction this. Okay, no, so okay, sorry, I said that I am writing this vector form. Actually what I can, a dipole is a uh, potential is a vector is a scalar quantity, so I cannot write this in vector form, but I can write those two. Okay, this dipole moment is a vector quantity times this unit vector. Okay, this is a unit vector, so I can represent it like this. Okay, but dipole will be a scalar quantity. So this is what P R cos theta. I can write this P R cos theta like this. Okay, okay, now electric potential of dipole is given by this, so I can this is how I represent the unit vector. Okay, in equation 2.15 is indicated approximately true only for distances large compared to the size of the dipole. So this is only true for when the size of the dipole is very small as compared to the length of the length where we have to find the potential. Okay, for a that's why we omitted the square terms in the derivation. You see, for a point dipole P at origin, however exact is however for a point dipole. Okay, the length is however is very small for a dipole, point dipole we have discussed earlier in the previous chapter. So in that case this is exact. Okay, from equation 2.15 potential on a dipole axis is given by, okay, you see the, it also depends, as you see on the equation 1 upon 4 pi epsilon naught P R cos theta by R square. Okay, this was the equation above, you see here P cos theta by 4 pi R square epsilon naught. So this is, it depends on theta, you see it depends on theta. So if cos theta is 0, theta is 0, then cos theta is 1, that will become this. So potential at an axial point will be, from an axial point the potential will be this much. Okay, this will be the potential. And for a equatorial point, theta will be what? Equatorial point is what? A point which is at a equal distance from the two charges. This is equal distance, equatorial point, for that theta is 90. Okay, the cos 90 is 0. Okay, so for a potential at a equatorial point is 0 and potential axial point is this much. Okay, so now the important contrasting feature of the electric potential of a dipole from that due to a single charge are clear from equation 2.8 2.15. Okay, so we'll discuss two features from here. The potential due to point charge depend not just on R but also on the angle between the position vector R and the dipole moment vector P. Okay, so you can see that dipole potential for the dipole depends on this R, the distance from the point on the center of the dipole, and also at the angle. Okay, at the angle it depends. It is however axially symmetry about P, that is if you rotate the position vector R about P keeping theta fixed, the point corresponding to P on the constant generator of the. Okay, so what's the meaning of this? I'll just draw it for you. Minus q plus q. So okay, this is a theta angle. Okay, and if I rotate this position vector, if I rotate this, okay, so it will follow, it will make a cone. This all points have the same potential. This is the meaning of this. Now the electric dipole moment falls off at large distances 1 upon R square, not as 1 upon R. You see from a for a point charge, for a point charge it was 1 upon 4 pi epsilon naught P by R, but for a dipole it is 1 upon R square. So you can see the potential decreases sharply as V for a dipole. Okay, so if you draw graph, you can explain it better like this. For a dipole, it would be like this. Okay, and for a point chart, it will be like this. Okay, somehow like this you can draw the graph. So I try to explain it, this equation and this dipole. Okay, if you like this video, please give it a thumbs up, and yeah, share with your friends. I try to make, whenever I get time, I try to make this, as I get requests for making these videos in English, Hindi also. So I have to make those videos in Hindi, but I'm trying. It is very difficult for me to make it in English, because my English is not very good. I'm trying. Okay, so have a little patience, and whenever, don't wait for my videos, because um, whenever I get time, I get time, I will make videos. So you will, after a week, you can check, then you will get 2-3 videos at least. I'll try. Okay, then thanks for watching.